Hello guys, welcome back to today's video. This is episode 6 of the Engineering Geology Webinar Series on stability of excavated rock slopes. In our previous videos, we discussed about cube slope method and also how to determine the steepest slope angles. Cube slope is one of the fastest techniques for assessing stability of excavated rock slopes. That's why we have been discussing about this method. At this point, we already have discussed about how to determine RQD, joint set number, joint roughness number, and joint alteration number. These are the parameters that are required to determine the Q slope value. There are other parameters that are also required to determine Q slope value. In today's video, we are going to discuss about the remaining important parameters that are required to undertake Q slope value calculation. Therefore, in today's video, I'm going to help you understand how to determine the parameters that are used to determine Q slope on site. Also, I will help you understand how to come to conclusion in your decision-making process on site. By the way, I used to work on site, on project site, and I understand the project site's conditions and how decisions are required from site engineers or engineering geologists or geotechnical engineers on site. So I'll give you insights on how to determine these parameters and come to conclusion. Like, subscribe, and share these videos with your friends. Let other geologists, engineering geologists, geotechnical engineers, and other civil engineers, contractors, and consultants also have the chance to see the videos. By the way, if you have any question related with this topic or also other engineering geology or geotechnical engineering topics that you would like me to discuss to you, please feel free to leave your comments on the comment section, also using my email address. If you would like to get lectures from other qualified professionals or experienced engineers or geotechnical engineers on Engineering Geology Webinar, please feel free to put their names and address on the comment section. Then I will review your comments and suggestions and do my best based on your recommendation, contact the professionals who give the lectures, and I will upload their lectures. Now let us delve into our today's discussion.
So we will record our ratings. This is RQD value. This is joint set number rating for joint set number. For set A, this is a roughness number. This is a rating for the alteration for joint set A. Rating is for roughness and alteration for joint set B. The next is parameter is O factor, that is orientation factor. For orientation factor, the description is given here: discontinuity, orientation factor, O factor. So these are the ratings for set A and for set B. If it is wedge failure, if it is only planar failure, you will consider only set A joints. So these are the description: very favorable orientation of the joints, quite unfavorable, very unfavorable, and extremely unfavorable conditions. These are the orientation conditions given. We have to correlate our joint sets planes with one of these descriptions. In my example, I have taken joint set A is the extremely unfavorable joint because it controls the instability condition here. So it is an extremely unfavorable condition. That means it is rating value will be 0.25 for set A. For set B, since set B is relatively is less adverse than joint set A, so it will be very unfavorable. So for joint set B, we have assumed joint set B is very unfavorable, and the rating from joint set B will be 0.8. Now we have RQD value, we have rating for joint set number, we have ratings for set A joints, joint roughness, joint alteration number, and also orientation factor for A, and for set B also roughness, alteration, and orientation ratings we have. That means we have already determined this parameter, two parameters, and these two parameters, 4, and also we have determined O factors O factors also, 5 parameters. Now we'll go for the environmental and geological condition, that is parameter 6. So in order to elaborate on the discontinuity orientation O factor, these are discontinuities that are very favorable to oriented joints forming cubical blocks. Those joints forming cubical blocks are considered as very favorable, and this type of joints is considered as quite favorable. And this type of joints that is unfavorable foliation planes that are dipping towards the valley are considered as unfavorable. Bedding planes that are dipping towards the valley are very unfavorable orientation. These are the foliation planes that are dipping towards the valley. These are vertical plane striking into the steep joints. These are steep joints. These are the bedding planes dipping towards the valley. They are very unfavorable. And these are the vertical joints, and the joints dipping into slope are favorable. These joints are favorable, but these ones are very unfavorable. When we come to here what we see is extremely unfavorable joints, because the joints are delighting onto the excavation. This is the excavation surface. This joint plane, if you see this joint plane, is both the joints are delighted or exposed on the excavated slope. So these are extremely unfavorable in both cases. The sixth parameter is environmental and geological condition, or JWIs. So the conditions given are desert environment, wet environment, tropical storms, and ice wedging. If you are working on the desert environment, you will consider this column. If you are working on wet environment, you will consider this column. If you are working on tropical environment, you will tropical storm environment, you will consider this column, these rating values. If you are on polar areas, on ice wedging area, you will consider these ratings. The other geological condition is stable structure, competent rock. So about the competency of the rock and about the geological structures. In our example, it is unstable structure. The structures, geological structures are unstable, but the rock is competent. So I just correlated my slope with this geological condition and the geological structural condition, but the environment could be either this or this or one of these. I just selected this environment, wet environment. So if it is wet environment, so JYs will be 0.5. Now we have already determined RQD, JN, JR, all the 6 parameters. We have left with only the 3 parameters of strength reduction factor of the slope. The 7th parameter is table 7 describes about the strength reduction factor of factor A, which is related with physical condition of the rock slope. So what we do is we will correlate our rock slope with these descriptions given here. These are the conditions given here. We will correlate it with these conditions. If it is one of these conditions describes the actual ground, then we will take the corresponding stress reduction factor A value from here. In our example, for this slope, I correlated this slope with loose blocks, because there are loose blocks, signs of tension cracks, and joints shearing susceptible to weathering, correlated with this description, physical condition description. So the corresponding strength reduction factor for A will be 5. Okay, then I will go for the strength reduction factor for B. Okay, so this is table 8 is about the strength reduction factor for B related with stress and strength, the ratio between the uniaxial compressive strength to the maximum principal stress. So how to determine this on site is, the first thing is we will determine the uniaxial compressive strength of the excavated rock slope by using a simple geological hammer. If I have a geological hammer, I am on this side, then I will use the geological hammer to determine the uniaxial compressive strength of the rock, the intact rock in the slope. So it is known as empirical field test. It is known as, based on empirical field test, it is possible to determine the unilateral compressive strength of the rocks, intact rocks in the slope, based on how many blows, the number of blows of geological hammer it requires to break a rock sample, easily can be determined using the geological hammer. So this can be done on site. So in our case example, for example, the unilateral compressive strength could be 50 megapascal, indicating moderately strong rock. We determine sigma c, so we have to determine sigma 1, and the sigma 1 can be determined by using this formula known as sigma vertical for an average unit weight of overburden rock, gamma, vertical and horizontal stresses at depths of h are denoted as, okay, at any depth. So the vertical stress can be determined, and the vertical stress is considered as the maximum principal stress, and the horizontal one is considered as minimum. We are interested with the maximum principal stress, that sigma 1 will be the vertical, that is gamma times unit weight times height. So we can measure this height or estimate the height, and also we can estimate the unit weight of this material, and then the unit weight times the height will give us sigma 1 value. In our example, for example, the unit weight considered as 27 kilonewton per meter cube, and the height 10 meter, and when we multiply this, we will get sigma 1 value is equal to 0.27 megapascal. So now we will determine the ratio between sigma c. This is 50 divided by sigma 1, 0.27, and it will be 185. That means it will fall within this range. So the description for the stress and strength description is moderate stress strength range. So the rating we take will be the 2.5 to 1. Let us take 2.5. Okay, so we have determined stress reduction factor A, that was 5, and we have determined here the stress reduction factor B, that is 2.5. We have to determine stress reduction factor C using table 9, that is the last table, and this is parameter is also the last parameter in determination of Q slope. So stress reduction factor C considers major discontinuity, and these are the descriptions, and the discontinuities. The major discontinuity in our case is set A are major discontinuities, and we can understand from this that set A joints are causing failures if unmanaged, because there are supporters, so these are failures. So we consider correlated this slope with this description. So the corresponding rating is 8. Okay, so when we see the stress reduction factor A is 5, okay, this is 5, stress reduction B is 22.5, and stress reduction factor C is 8. So we will take 8 for this parameter, because we will take the maximum stress reduction factor, and we will insert 8 here. Now we can insert all the determined parameters in this equation. Okay, this is RQD inserted here, this is JN rating here, and joint sets A. For joint set A, we will calculate R over GR over GA times O factor of A, and for joint set B also do the same, and we will multiply it like this. So this is be the calculation. Cube slope is equal to 61 over 12. 2 over 3. 2 is what? 2 is JR2. GR is 2, and 3 is JA. 2 over 3 times O factor is 0.25 for this is for joint set B. So this one is finally 0.5 divided by 8 means 0.5 is JYs, and 8 is stress reduction factor C. So finally we will get the Q slope value that is determined in this case is 0.635. And using the Q slope value in this formula, inserting this value in this formula, we can get the steepest slope angle, that is in the present case it is 41 degree. Like this, you can conduct easily determine the steepest slope. According to this, this finding indicates that the steepest slope, maximum slope angle, should be 41 for maintenance-free stable slope of slope cutting in this type of material. Okay, can do easily implement Q slope like this. Thank you.
ወደ ተመልካቾች ይህንን ቪዲዮ ያያችሁ ተመልካቾቻችን ተመሳሳይ ወይም የተሻለ ቪዲዮ በመስራት በኢንጂነሪንግ ጂኦሎጂ ዌቢናር በሚዲዮ ቻናል ላይ እንዲቀርብ ለማገዝ በዚህ ይህንን ቻናል ሰብስክራይብ በማድረግ እንድታግዙ በትህትና ጠይቃችኋለሁ።